What if everything you see, everything you experience is just a shadow of a far grander reality? Our entire existence unfolds in just 4 dimensions. 3 of space, length, width, height, and 1 of time. But what if there are dimensions all around us that we simply cannot perceive? Einstein's theory of relativity revealed that space and time are woven together into a 4-dimensional fabric called space-time. This framework governs our daily lives and underpins all of modern physics, but cutting-edge theories like string theory and M-theory suggest something extraordinary. What does it mean to exist, to occupy a position in space, to move through a sequence of moments? At its heart, our reality is structured by dimensions. A dimension is a fundamental coordinate, a direction of measurement. We instinctively understand the 3 spatial dimensions that define our world: the left-right of the x-axis, the up-down of the y-axis, and the forward-backward of the z-axis. Together they create the 3-dimensional space we inhabit. But there is another equally crucial component: time. It is the 4th dimension, inextricably woven with space into a single continuum, as Einstein revealed. Every event, from the flicker of a candle to the explosion of a star, has a unique address in this 4-dimensional fabric of spacetime. For centuries, this 4-dimensional reality seemed complete, the entire stage on which the drama of the cosmos played out. But what if our perception is limited? This is where the power of pure mathematics illuminates paths our senses cannot follow. Long before physicists had a use for them, 19th-century mathematicians like Bernhard Riemann began to explore the abstract possibility of spaces with any number of dimensions. They proved that the familiar rules of geometry could be logically extended, creating self-consistent worlds with 4, 5, or even more spatial axes. These higher dimensions, while invisible and intangible to us, emerge not from fantasy, but from the rigorous language of equations. They suggest a universe far grander and far more complex than the one we can directly perceive. So, if these extra dimensions exist, where are they hiding? The answer could be a matter of scale. Imagine a garden hose stretched across a vast lawn. From a great distance, it appears to be a simple one-dimensional line. But if you were a tiny ant living on its surface, your reality would be very different. You would perceive 2 dimensions of travel. The long one we see from afar, and a second tiny circular dimension curled up on itself. String theory proposes that extra dimensions could be just like this, curled up or compactified to a size so infinitesimally small that they are completely hidden from our everyday experience. This idea is central to M-theory, a leading version of string theory, which requires 7 extra spatial dimensions for its mathematics to be consistent. This means our universe would possess a total of 10 spatial dimensions, plus time. In the theory, these 7 hidden dimensions are curled up into incredibly complex, elegant geometric shapes known as Calabi-Yau manifolds. They are compactified down to the Planck length, about 10 to the power of -35 meters. To put that in perspective, if you were to scale up a single atom to the size of our entire observable universe, one of these manifolds would be about the size of a tree. They are the hidden, subatomic architecture of space itself. This intricate, hidden geometry isn't just decorative, it dictates the very laws of physics. Within this 11-dimensional space, the fundamental constituents of reality are not particles but tiny, vibrating filaments of energy, strings. Just as a violin string vibrates at different frequencies to produce different musical notes, these strings vibrate in different patterns. The specific shape of the Calabi-Yau manifold constrains which vibrations are possible. One pattern manifests as an electron, another a photon, yet another a quark. All the particles and forces we see are simply the different notes these strings can play, a cosmic symphony resonating through the hidden dimensions. But there is an alternative, equally mind-bending possibility. What if the extra dimensions aren't small at all? What if they are large, perhaps even infinite? This is the idea behind braneworlds scenarios. In this model, our entire 4-dimensional universe is confined to a membrane or brain, floating within a much larger, higher-dimensional space called the bulk. All the matter and forces we know are stuck to our brain, unable to leave. But one force might be different: gravity. As the very curvature of space-time, gravity might not be confined, allowing it to leak out into the bulk. This could explain why gravity is so much weaker than other forces. Its influence is diluted across these vast, unseen dimensions. This means other brains, other universes could be floating parallel to our own, separated by a microscopic distance in a higher dimension, forever beyond our reach but perhaps not beyond our detection. The concept emerged in the 19th century with mathematicians like Bernhard Riemann, whose work on curved geometry influenced Einstein. In 1919, Theodore Kaluza proposed a fifth dimension to unify gravity and electromagnetism, an idea refined by Klein, who suggested this dimension was compactified into a microscopic loop. To understand our predicament, consider Edwin Abbott's Flatland. Two-dimensional beings perceive a sphere passing through their world as a circle that grows and shrinks, unable to grasp its three-dimensional nature. Similarly, a four-dimensional tesseract, when projected into our space, appears as a distorted, impossible cube that confounds our intuition. Our experience of reality is filtered through senses sculpted by evolution, not for revealing fundamental truths, but for survival. Our eyes perceive only a tiny sliver of the electromagnetic spectrum, visible light, because that's what helped our ancestors navigate a three-dimensional world. We are blind to the ultraviolet world of bees or the infrared vision of snakes, a stark reminder that our perception is a customized user interface, not a direct window onto reality. This evolutionary focus makes our senses ill-equipped for the scales where extra dimensions might exist. Theories propose two scenarios. They could be microscopic, curled up so tightly they are imperceptible, like the circular dimension of a garden hose that appears as a line from a distance. Or, they could be vast macroscopic brains, parallel universes existing alongside our own, but in a direction our senses cannot point or interact with. To probe these microscopic dimensions, we must use energy. In particle physics, higher energy acts like a more powerful microscope. To see a curled-up dimension would require energies approaching the Planck scale, a staggering 10 to the 19th gigaelectron volts. Our most powerful machine, the Large Hadron Collider, is a quadrillion times less powerful. This technological chasm leaves these tiny realms completely hidden from our direct view for the foreseeable future. For large, parallel dimensions, our best hope is gravity. Unlike other forces confined to our 4D brain, gravity might leak across all dimensions, explaining its weakness. Experiments meticulously measure gravity at short distances, looking for deviations from the inverse square law. If gravity behaved differently at the sub-millimeter scale, it would be powerful evidence. So far, however, it has behaved exactly as predicted, offering no clues to a larger reality. Beyond physical limits lies a profound cognitive barrier. Our mental architecture is built on a four-dimensional framework, 3 of space, 1 of time. Our language is filled with spatial metaphors, our intuition for geometry is fundamentally three-dimensional. We can easily picture a cube, but trying to truly visualize its four-dimensional equivalent, a tesseract, causes our minds to falter. We can only represent its shadow, not perceive the object itself with our mind's eye. This is where abstract thought becomes essential. Since we cannot intuitively grasp higher dimensions, we must describe them mathematically. Physicists use powerful tools like tensor calculus to work with the properties of these spaces, without needing to visualize them. They can calculate how geometry behaves in a 10-dimensional universe through pure logic. This is a monumental achievement, but it also underscores the gap between our evolved intuition and the stranger reality that mathematics allows us to glimpse. The search for evidence begins at the smallest scales. At the Large Hadron Collider we hunt for Kaluza-Klein particles, hypothetical, heavier echoes of familiar particles. If extra dimensions exist, the LHC's immense energy could give a particle momentum in a hidden dimension, manifesting as a new heavy particle. Its signature could be energy seemingly vanishing from our detectors, having escaped into the higher dimensional bulk. String theory's requirement of 10 or 11 dimensions ensures mathematical consistency, eliminating anomalies that plague other theories of quantum gravity. This isn't an arbitrary choice, it's a necessity to prevent paradoxes. The theory proposes these extra dimensions are compactified, curled up into unimaginably tiny shapes at every point in space, far too small for us to perceive directly. At cosmic scales, anomalies in the cosmic microwave background, the faint afterglow of the Big Bang, could hold clues. Unexpected temperature fluctuations like vast cold or hot spots could be cosmic scars. These wouldn't be from processes within our universe, but bruises left by a collision between our brain universe and another, drifting through the higher dimensional bulk. The Event Horizon Telescope's images of supermassive black holes could reveal deviations from four-dimensional predictions, hinting at higher dimensional effects. In our 4D universe, a black hole's shadow should be nearly circular. But if gravity leaks into extra dimensions, it could subtly warp the shape of that shadow, providing a telltale sign. Perhaps the most compelling clue is gravity's mysterious weakness. It is staggeringly feeble compared to the other forces. Why is it 10 to the 39th times weaker than electromagnetism? This hierarchy problem is one of the greatest unsolved puzzles in physics, and extra dimensions offer a tantalizingly elegant solution. The answer might be that gravity leaks into macroscopic extra dimensions. In this model, our universe is a brane floating in a higher dimensional space. While other forces remain confined to our four-dimensional brane, gravity is not. It spreads its influence across all dimensions, and feels weak to us because most of its power has leaked away into this vast, unseen bulk. Next-generation colliders like the proposed Future Circular Collider could reach 100 tera-electron volts, potentially producing micro-black holes or exotic particles that would confirm extra dimensions. The James Webb Space Telescope and future observatories could detect signatures of brane interactions or higher-dimensional gravitational effects in the cosmic microwave background. Augmented reality tools can simulate higher-dimensional objects, allowing us to visualize Calabi-Yau manifolds and explore the geometry of compactified dimensions. Brain-computer interfaces could translate higher-dimensional data into sensory signals, potentially enabling direct perception of dimensions beyond our natural capabilities. Artificial intelligence can analyze high-dimensional datasets, revealing patterns in spaces our minds cannot directly comprehend. New mathematical tools and visualization software are making the invisible visible, bridging the gap between abstract theory and intuitive understanding. Some speculative theories suggest consciousness itself might access higher dimensions. Meditation, altered states, and transcendent experiences hint at perceptual capabilities beyond our ordinary awareness. Genetic engineering could theoretically enhance our sensory or cognitive capacities, enabling perception of microscopic or macroscopic dimensional effects. Wormholes or quantum entanglement devices could provide indirect access to higher dimensions, allowing us to explore the bulk that surrounds our brain. These technologies remain speculative, but they could emerge from breakthroughs in quantum gravity and our understanding of space-time itself. Pursuing higher dimensional awareness raises profound ethical questions. These experiments demand vast resources and could challenge fundamental beliefs about reality itself. Transparent communication and public engagement are crucial as we push the boundaries of human knowledge and potentially discover dimensions beyond our current understanding. The possibility that our four-dimensional universe is embedded in a higher dimensional reality represents one of the greatest frontiers in modern physics. Through advanced experiments, technological innovation, and philosophical reorientation, we may transcend the barriers that confine us to four dimensions. As we expand our perception, we may uncover a cosmos far richer than our four-dimensional experience, redefining our understanding of reality and our place within an infinite, multidimensional universe.